I want you to imagine, just for a second, that you are standing on the floor of an immense manufacturing plant.
Mm-hmm.
You've got a pen in your hand, and you are staring at a piece of paper. And, well, this isn't just any piece of paper. It is a capital expenditure authorization, a CapEx request for a multi-million-dollar heavy machinery purchase.
Right. That's a massive decision to be making.
Oh, absolutely. You are about to buy a new factory workhorse. But here's the terrifying part. If your engineering team misjudged the specific spindle architecture that you need for the work you are doing, the result of signing that piece of paper isn't just some minor administrative hiccup.
No, not at all.
Right. I mean, we were talking about violent tool chatter echoing through the facility, catastrophic cutter failure where expensive metal just shatters into shrapnel, and, severe production bottlenecks that could cost a fortune.
Yeah, and when you're operating at the scale of heavy-duty manufacturing, the margin for error during that procurement phase is practically zero. You cannot simply box up and return a machine the size of a two-story house if it fails to hit your required tolerances. It just doesn't work that way.
It really doesn't. And that brings us to the mission of today's deep dive. Today, we are decoding a gigantic stack of factory engineering manuals, cutting tool white papers, and heavy machinery spec sheets to really understand one of the most critical choices in modern manufacturing.
The choice between a fixed spindle horizontal machining center and a traveling spindle.
Exactly. The fixed spindle is often called an HMC, and the traveling spindle is known as a horizontal boring machine. So our goal today is to completely break down the mechanical DNA of these two colossal machines. We want you to be able to perfectly match the machine's anatomy to your exact production requirements, whether you were actually signing that CapEx check or, you just love understanding how gigantic things are built.
Because choosing the right spindle design dictates your shop's entire operational strategy. I mean, it controls your cycle times, the sheer speed at which you can pump out parts, and it governs your surface finish capabilities. Yeah, it is the absolute beating heart of the factory floor.
Okay, let's unpack this. Before we can even begin to understand how these machines rip through incredibly tough steel alloys, we really have to look at the kinematics.
Right, the movement.
Exactly. We need to understand the fundamental differences in how they physically move to reach the part they are cutting. So, let's start with the fixed spindle. When we say fixed, we mean the rotating shaft that actually holds the cutting tool is locked entirely inside a heavy iron casting.
Completely encased.
Yes, there are absolutely no internal sliding parts inside that spindle head. Instead of the spindle reaching out, the entire gargantuan iron column, or sometimes the whole work table itself, moves along your standard X, Y, and Z axes to feed the tool into the metal.
Which is a huge structural advantage.
It is, and because the head itself is acting as one solid block, it moves incredibly fast. We are talking about a heavy-duty machine that can zip around and perform tool changes in a matter of, 2 or 3 seconds. It is designed for pure speed and brutal, simple reliability.
Yeah, a fixed spindle essentially eliminates a major variable in mechanical movement. But, that simplicity changes dramatically when you look at the traveling spindle architecture from our source materials.
Oh, definitely.
A traveling spindle introduces a completely new direction into the mix, which engineers call the W-axis.
The W-axis. Okay.
Right. So in this setup, the main machine column stays perfectly anchored. Instead of the whole body moving toward the metal, a central boring bar, which is a thick steel cylinder called a quill, or sometimes a large square ram, slides outward from the main headstock.
Just sliding right out.
Exactly. It physically extends forward, leaving the safety of the main casting to plunge directly into deep cavities.
Wait, reading about this W-axis extension makes me kind of nervous. The engineering white papers paint a really vivid picture of this fixed spindle as a heavyweight boxer.
Oh, I like that analogy.
Yeah, like a boxer steps their entire body weight into a punch to deliver maximum power and stability, right? The fixed spindle moves its whole body. If I have the option to use that kind of brute structural force, why on earth would I want a traveling spindle machine that just sits completely still and slowly extends a vulnerable, isolated arm out into open space?
It does seem strange at first glance.
It sounds completely counterintuitive to the physics of heavy cutting.
Well, the physics of heavy machinery actually prove your concern to be completely valid in certain scenarios. But the requirement for that extending arm comes down to one non-negotiable factor: reach.
Reach, okay.
Think about the physical constraints of standard Z-axis travel limits on a fixed spindle. The bulky iron casting holding the spindle can only move forward so far before it physically collides with the workpiece.
Ah, right. It just crashes into the part.
Exactly.
Yeah.
Now, picture yourself tasked with machining a multi-ton ship engine block or a deep subterranean pump housing. You have features in internal bearing journals located 3 feet deep inside a narrow cavity.
Wow, 3 feet.
Yeah, the bulky casting of a fixed head simply cannot fit inside. The traveling spindle becomes completely mandatory there. You need that specialized quill to reach deep into the darkness where the main machine column cannot follow.
So the fixed spindle is a speed demon throwing its whole body around, and the traveling spindle is a specialist reaching into tight spaces.
That's a great way to put it.
But speed creates violence. What actually happens at the exact microscopic moment when a machine moving that fast slams a cutting tool into a wall of solid steel? Because we are talking about heavy face milling and side cutting, ripping off huge chunks of metal.
What's fascinating here is how that physical movement we just discussed dictates side rigidity. Let's look at the fixed spindle first.
Okay.
Because it lacks an extending W-axis, a fixed spindle keeps its primary support bearings right behind the cutting edge. There is virtually no empty space between the tip of the tool and the heavy iron frame.
It's all packed tightly together.
Right. So the moment that cutter hits hard metal and begins experiencing those violent radial forces, the solid iron casting instantly absorbs the shock. The energy transfers directly into the machine's foundation.
Oh.
It acts as one unyielding block, making it exceptionally stable for aggressive material removal during heavy side cutting.
I have a theory about the traveling spindle then, based on the physics models in the cutting tool white papers.
Okay, let's hear it.
So if I stick a heavy steel arm out into midair on that W-axis and try to cut sideways, isn't it going to act exactly like a long diving board? Like if you walk to the end of a diving board and push sideways, it immediately bounces and twists. There's no rigidity out there. Doesn't that flex cause terrible vibrations that would just destroy the metal surface you were trying to smooth out?
Yeah, you hit the nail on the head. The physics formulas in the spec sheets confirm your diving board theory perfectly.
I knew it.
A fully extended traveling spindle is inherently weak when subjected to heavy side-cutting forces. The support bearings are simply too far away from the cutting action, and that microscopic bending introduces chatter.
Right, chatter.
And chatter is a self-sustaining vibration that destroys surface finish, chips the cutting inserts, and can ultimately snap the tool right in half.
That sounds incredibly expensive.
It is. But we have to look at the inverse scenario. If you need to bore a deep hole, a fixed spindle is actually the far worse option.
Wait, why? If it's a solid block, shouldn't it be better at everything?
Because of how you have to bridge the gap. To reach deep into a cavity with a fixed spindle, you cannot extend the head, so you are forced to use an exceptionally long, thin tool holder.
Oh, I see.
You are basically attaching a long, skinny stick to a heavy block.
Yeah.
That long tool holder is highly susceptible to bending and snapping.
That makes sense.
In contrast, the thick, heavy steel ram of a W-axis on a traveling spindle is vastly thicker and mechanically stronger for deep hole boring than any long tool holder could ever be.
Yeah.
It is engineered specifically for axial loads, meaning pushing straight ahead.
Okay, that clarifies the trade-off. Fixed is better for sideways forces close to the face, and traveling is better for pushing straight ahead into deep pockets.
Exactly.
And I noticed something fascinating in the tooling white papers about how you maximize that fixed spindle. Because the machine casting is so rigid, you can't just slap an old-school tool holder into
No,
it.
definitely not.
Standard tool tapers just pull the tool from the back, leaving a tiny microscopic gap at the face. Instead, the white papers stress the use of dual contact tapers, like Coromet Capto or HSK tooling.
And the mechanism behind those dual contact tapers is brilliant.
It really is. I was reading how they work. Instead of just wedging into the cone, these specific tool holders are engineered to pull tight inside the taper while simultaneously pressing perfectly flat against the front face of the spindle.
Right, making contact in two places at once.
Yes. It locks the tool so solidly that the interface essentially disappears. The cutting tool becomes a literal extension of the machine casting itself. You don't see that as much on traveling spindles, which typically rely on standard heavy taper blocks because, well, their primary job is slow, deep, boring, not ultra-rigid side milling.
Yeah, the tooling interface always has to match the machine's primary mechanical strength.
Yep.
You utilize dual contact tapers to exploit the sheer rigidity of the fixed spindle.
Eh.
It is about optimizing the entire chain of energy transfer from the concrete floor through the iron casting straight through to the cutting edge.
Here's where it gets really interesting.
Yeah.
We've established the physical traits. Fixed spindles give you rigid speed. Traveling spindles give you deep reach.
Right.
But the factory engineering manuals show how these physical traits completely alter the layout of a factory floor. They dictate the types of workpieces a shop can even bid on. Let's look at a high-volume fixed spindle setup. I was blown away by the level of automation described here. Imagine a medium-sized prismatic part. And by prismatic, the manuals mean a blocky, multi-sided shape, like a heavy-duty engine manifold or a transmission housing, something that fits inside a hypothetical cube.
As opposed to a round part you turn on a lathe.
Exactly. I mean, right. So this prismatic part is mounted on what's called a tombstone fixture, which is essentially a tall, multi-sided metal tower. This tombstone is locked onto a fast B-axis rotary table. The fixed spindle zips in, machines one face of the part, the rotary table quickly indexes and spins the part 90 degrees, and the spindle immediately cuts the next side. Chips are flying everywhere, but they fall straight down into an auger system below.
Highly efficient.
And the best part, while the spindle is aggressively cutting metal inside the enclosure, an automatic talent changer is working outside. An operator is preloading the next raw casting onto a second tombstone.
So there's almost zero downtime.
Yes. The exact second the first part is finished, the doors slide open, the pallets physically swap places, and the spindle goes right back to cutting. You are keeping that spindle engaged and cutting metal 85% of the day. It is a high-speed ecosystem designed for relentless efficiency.
That continuous, relentless production is the ultimate economic goal of the fixed spindle architecture. But contrast that high-speed pallet-changing environment with a facility utilizing a traveling spindle.
Okay, totally different vibe.
Completely different. Think about colossal asymmetrical parts. You cannot put a 50-ton wind turbine hub or a submarine bulkhead on a tombstone fixture.
Oh, an automatic pallet changer would be crushed instantly.
Exactly. Parts of that magnitude had to be lowered via heavy overhead cranes to sit directly on the factory floor, secured to heavy-duty steel floor plates embedded in the concrete.
So it's almost like comparing a high-speed drive-through lane to a dry dock for a cargo ship.
I like that.
The fixed spindle is the drive-through, get the part in, spin it, cut it, swap it out. The traveling spindle is the dry dock. The colossal part comes in and it just sits there.
Very true.
But that brings up a huge logistical question. If a 50-ton wind turbine hub is completely stationary on the floor plates and the traveling spindle is just poking a steel bar into it, well, how do you do complex machining on the outside of the part?
Ah, that's the real trick.
Yeah, if I need to cut a perfectly flat flange or thread the outside of a gigantic pipe, I can't spin the part like I do in the fixed spindle's rotary table. It's too heavy.
That exact dilemma is where the traveling spindle utilizes a highly specialized mechanism called a U-axis facing head.
A U-axis facing head.
Yeah. It is a programmable attachment that mounts directly to the front of the traveling spindle, and it essentially turns the milling machine into a giant lathe.
Wait, how does that mechanically work if the part isn't spinning?
Because the workpiece is too colossal to spin, the U-axis facing head spins the tool around the stationary part.
Oh, wow.
But it does more than just spin. While the head is rotating, an internal mechanism physically pushes the cutting tool outward along a radial track. So the tool is spinning in a circle and simultaneously sliding outward, creating a perfectly flat face on a stationary object.
That is wild.
It gets better. By synchronizing that outward sliding motion with the W-axis pushing forward, you can even cut complex threads on the outside of these massive components. It is a brilliant mechanical inversion of traditional machining.
The tool spins around the part because the part is too heavy to spin around the tool. That is incredible. But of course, with all this extreme engineering comes the reality of keeping these machines running.
Always a factor.
I was reading through the maintenance sections of the engineering manuals, and the specific ways these machines break down and inflate your total cost of ownership, or TCO, are entirely different.
Yeah, the maintenance profiles are as different as the machines themselves.
Let's look at the fixed spindle first, because this genuinely blew my mind. Because this machine is built for speed, the spindle can easily spin at 20,000 RPM.
Which is incredibly fast for heavy iron.
At those velocities, friction creates heat, and heat is the absolute biggest enemy of precise engineering. To survive, the manual strictly requires a delicate oil-air mist system to lubricate and cool the bearings.
Right.
But here's the catch. The compressed air in the factory must be immaculately dry. The manual states that if even a single drop of water makes it into the factory airline and gets blown into that 20,000 RPM spindle, the water instantly flashes to steam from the heat.
It's basically a microscopic explosion.
Exactly.
There.
That microscopic steam explosion blows the lubricating oil away from the ball bearings. Without oil, at that speed, the bearings friction weld themselves together in a matter of seconds. Thousands of dollars and days of downtime caused by a single drop of humidity.
It really highlights how highly sensitive a system operating at those parameters truly is.
And it doesn't stop there. The drawbar, the internal mechanism holding the tool up into the spindle, relies on stacks of heavy Belleville springs. The sources mandate that these springs must be tested with a force gauge weekly. Why? Because over thousands of tool changes, the metal springs experience fatigue and lose their clamping force.
Which is dangerous.
Yeah, if the tool is held even slightly loose, it creates microvibrations, a phenomenon called fretting. The hardened steel tool chatters against the inside of the spindle, slowly wearing away the perfectly ground angles until nothing fits tightly anymore. The taper is ruined.
If we connect this to the bigger picture, the fixed spindle operates exactly like a high-performance Formula One car.
Oh, totally.
It requires extraordinarily pure inputs, immaculate air, exact clamping forces, and constant microtuning to maintain its speed. Now, observe the brute force maintenance requirements of the traveling spindle.
Okay.
We're dealing with a heavy steel bar sliding in and out of the main headstock all day long in an environment flooded with sharp metal chips.
That sounds like a recipe for disaster.
It can be. The traveling spindle relies on hydrostatic sliding bearings. Think of it like a heavy-duty air hockey table. The heavy steel W-axis bar is literally floating on a micro-thin layer of highly pressurized oil pumped in from the machine. There is zero metal-on-metal friction.
Wait, but if it's sliding in and out, how do you protect that oil layer from all the metal chips flying around?
That is the vulnerability. To protect those bearings, the traveling spindle uses heavy rubber wiper seals that physically squeegee the steel bar clean as it retracts back into the housing.
Ah, okay, like windshield wipers.
Precisely. If one of those rubber seals tears or degrades, sharp metal chips are dragged straight inside the housing. Those chips will score the metal, disrupt the pressurized oil film, and rapidly destroy the hydrostatic bearings. Maintaining the wiper seals is a constant, messy battle against physical contamination.
Okay, using rubber seals to wipe away metal chips makes total mechanical sense. But reading through the spec sheets, I kept wondering about a force that is even more unavoidable than metal chips.
Gravity.
Yes. What about gravity? If you have a gigantic steel cylinder extending 3 feet outward in midair all day long, reaching deep into ship engines, I mean, a steel bar that heavy has to naturally sag under its own weight, doesn't it?
It absolutely does. In structural engineering, this is defined as geometric droop.
Geometric droop. Got it.
It is unavoidable physics. You cannot build a steel bar long enough and heavy enough that it won't experience some level of microscopic bending due to gravity.
So how do they fix it?
To combat this, the maintenance protocol requires a process completely alien to a fixed spindle. Once a year, a specialized technician sets up a highly sensitive laser calibration system. They measure the exact microscopic amount of droop at various points of extension along the W-axis.
What do they do with that data?
That specific sag profile is fed directly into the machine's CNC control. The computer memorizes the exact curve of the droop.
Oh, wow.
Yeah, as the operator extends the boring bar during a cut, the machine's internal axis continuously and microscopically adjust the entire spindle upward in real time to perfectly counteract the gravitational pull.
That is incredible.
This digital compensation guarantees that even when fully extended into a deep cavity, the resulting hole remains perfectly straight and mathematically accurate.
The machine literally maps its own physical weakness and fights gravity in real time just to keep a hole perfectly straight. That is absolutely wild.
It's modern engineering at its finest.
So what does this all mean? If we are looking back at that CapEx authorization paper on the factory floor, the ultimate takeaway from our deep dive is clear. You choose a fixed spindle architecture for fast, rigid, high-volume production of prismatic parts. You want that high-speed drive-through lane that makes money by swapping pallets and keeping the spindle aggressively cutting metal 85% of the day. Conversely, you choose a traveling spindle when your geometry demands it, when you need to reach deep inside immense stationary industrial components that require overhead cranes and floor plates just to exist in the shop.
Exactly.
You have to perfectly match the mechanical anatomy of the machine to the exact geometric challenges of your work.
Whether you are a manufacturing engineer actively plotting out a massive factory upgrade, or you are simply someone fascinated by the extreme physics of how our modern world is built, understanding the why behind these architectural choices is the ultimate shortcut to being well-informed.
I completely agree.
Knowing why a fixed spindle utilizes dual-contact Cormac Capto tooling, or why a traveling spindle relies on real-time laser droop compensation, allows you to look past the heavy iron. It allows you to understand the invisible forces, chatter, geometric droop, and thermal expansion that engineers are constantly battling on the factory floor.
It really is an endless war against the physics of cutting tough steel. But before we wrap up this deep dive, I want to leave you with a final provocative thought to ponder on your own.
Oh, I'm intrigued.
Throughout our entire exploration of these source materials, the one constant variable has been the material itself. Tough steel alloys. We've discussed how cutting these heavy metals necessitates these gargantuan iron structures, dual contact tapers, and thick boring bars just to fight vibration and deflection.
Right, because steel is unforgiving.
But what happens as materials themselves begin to evolve? Think about the aerospace or green energy sectors. What if tomorrow's immense industrial components, the next generation of wind turbine hubs or aircraft bulkheads, are manufactured from incredibly tough but next-generation lightweight composites?
That's a great question.
Materials that simply don't generate the same violent, heavy cutting forces as traditional steel. If those cutting forces drop dramatically, will this fundamental, rigid divide between fixed and traveling architectures begin to blur?
It very well might.
Or, as the factory floor continues to evolve with new materials, will the manufacturing world demand an entirely new, third type of spindle design that completely abandons heavy iron altogether? Think about that the next time you picture signing a multi-million-dollar CapEx check. The rules of the factory floor are written in iron, but, iron can always be melted down and recast.
Beautifully said.
Thanks for joining us on this deep dive. See you next time.